Hello, everyone. Today, I'm going to share a paper on power system synthetic data generation. The name is Multiload-GAN. You see, it is a generative model, meaning a GAN-based model to generate a synthetic node profile group. And the special thing is it considers the spatial temporal correlations between the nodes in this group. The right figure here shows a typical power system. You see there are some generators here, and after the generation, we have a transmission network to transfer the load from the generator to the customers. And here, this is a substation. Down here, the green part, we call it the distribution system. Our work mainly focus on the distribution work here. There are some customers here, all kinds of customers, including residential, commercial, industrial, all type of customers. Each customer, their consumption is measured by the smart meter. So with the measurement of smart meter, you get the load profile of each household, meaning the load profile tells you how much you consume the power from the grid in each time step. This kind of load profile is important for power system, especially the power distribution system analysis, operation, planning, all kinds of research. But in reality, our researchers cannot get so much load profile data because of the privacy issue. For example, you have the smart meter data, you can derivative a lot of privacy information for the consumers. For example, you based on the peak and the valley hour of their consumption, you know when the customer is going out and when it's going to stay at home. And also based on the daily or weekly profile, you can identify whether or not this household own electrical vehicle. So all those informations are very sensitive, and all them are the privacy information here. So due to those reasons, the utilities cannot share enough real load profiles to us, even for the research perspective. So a solution for this problem is to generate some synthetic data to create more operation scenarios. There have been a lot of methods to do the synthetic data generation, but there is one problem. All of them can only generate a load profile, only one profile at one time. Meaning, you see, there is a group of nodes served by the same transformer. This is the transformer in the red box. Typically, in this case, Rose customers are geographically close to each other. It means that they may have the same weather pattern. The weather is, especially the temperature, is have great impact on the load consumption level. For example, in extremely hot summer day or extremely cold winter day, the power consumption is much higher than the other days, right? So another thing is, since they are close to each other, they may have similar demographic characteristic. For example, their income level or the living pattern, that kind of thing, might be close to each other. This shows they have similar user pattern. So based on those reasons, we see the loads supplied by the same transformer may have some high level or the group level characteristics. This kind of group feature may not be easily explicitly described, but it does exist. So our task is to generate a group of node profiles and preserve this kind of group level feature. This page shows you the main difference between our proposed method and the existing method. Suppose you are required to generate a cat image and a family of cat image. So for the traditional methods, you can generate one image at a time and you repeat it multiple times, you get a lot of cat images, and then you get a synthetic database. If you need a family cat, you randomly pick some cats from the database, and then you get a group. But in this case, it's hard to see it's a cat family because those cats are randomly selected and they are all different. So in our method, we generate a group in one time. I mean, generate n node profiles simultaneous. So in this way, we can get some cats that share some common feature or some high level group level feature so that we can see those cats are from the same family. So the similar thing for a group of node profiles. This is the overall configuration of our model. It is a GAN-based model. We see there are two parts. The first part is generator, and the second part or the second network is discriminator. We can regard the generator as a teacher. I'm sorry. We can regard the first the generator as a student, and we see the discriminator as a teacher. Then at the beginning, the student is going to solve some problem and get the answer. The answer goes here, and the teacher see both the answer from the student and the solution of the work. So the teacher is going to evaluate how well the student has done. At the beginning, both the student may do the work not as good, and the teacher is going to not going to use so strict rule to evaluate students' work. But when the training going on, the student is going to getting better and better and going to generate more and more good results. And teacher is going to use more and more strict evaluation criteria to grade the work of the student. So by the end of training, the student is going to get a higher and higher level so that he can generate more and more realistic synthetic data. So to be more technically, in our case, we take the random noise as the input of the generator, and the output is not directed to the node profile group. We directly generate image, and then we decode it to the node profile group. For the discriminator, from the real data set, we take the node profile group, and then we encode it into an image. And then to distinguish the difference between the synthetic generated data and the real data. So in this way, we can transfer the time sequence node profile into an image so that we can use some image processing technologies to deal with this kind of power system time sequence data processing task. This is the detailed information about the encoding and decoding method. For each single node profile, we encode into an image bar, means only one row. And for multiple node profiles, we can encode it into a multiple row, meaning this is an image. For each value in the node profile, we encode it into a vector consists of 3 values. And those 3 values are mapped into the RGB 3 channels. And also the temperature, I have mentioned before, the temperature is strongly correlated with the consumption level. So we encode the temperature as the 4th channel. So by the end of the day, we transfer the node profile group together with temperature into a 4-channel image. The right table shows the value mapping method used in the encoding and decoding method. Since the model is well trained, we need to evaluate it. But there is a unique challenge. Imagine you generate a family cat. You can very easily distinguish which one is a cat family and which one is not. Because our human being is sensitive to image, we can easily do it by visual inspection. But for the load sequence data, it's hard. Even for those highly experienced experts in power system domain, they cannot distinguish which one is generated, which one is real in real time, in a short time. So this is the main challenge here. We need to design some evaluation criteria here. There are two categories. The first is the statistical based. We design both household level and the transformer level, meaning the group level feature evaluation. And the second category is machine learning based. We train a deep learning classifier to identify whether or not this group of node profile is served by the same transformer. This is basically a classification task. So I'm not going to show you the results. The results shows our method performs much better than the baseline method. If you are interested in more detail about this paper, please refer to this publication. This paper is published on the IEEE transactions on smart grid. Here is also a GitHub site. This is my personal GitHub site. You can check the source code of this paper. And also there is another GitHub repository that shares different algorithms developed in our group. Most of them are related with synthetic data generation. Also, there are some data generated by those algorithms. So please refer to them if you are interested in them. Okay, this is what I want to present today. Thanks for watching.